My name is Tugrul Balci, and I'm a graduate student at University of Pittsburgh. And I will be talking about FPseg, which is a fast Poisson segmentation algorithm for genomic annotations. A genome consists of regions that have different functions. For example, we have intron-exon regions, and as we all know, exons are translated into amino acids while introns are not. And then there are regions that regulate inhibit gene translation, such as promoter enhancer regions. And then there are regions where some proteins bind to serve a function, such as CTCF. Since all these regions have very important functions, being able to identify these regions is a very important task. Luckily, now we have a plethora of epigenetic data. All we need to do is come up with algorithms. So we developed FPseg with several things in mind. First of all, we wanted it to be scalable. One of the problems that the current segmentation algorithms have is that they take days to segment the genome, and usually the data is bent, so they work with lower resolutions. So we tried to avoid this. Another criterion was interpretability. We wanted all the clusters to be biologically meaningful. We wanted genomic regions, such as the ones I mentioned earlier, to be enriched in these clusters. And finally, we want it to be easy to use. We wanted to use row count data directly. Also, we want to use cross-validation methods to pick hyperparameters so the users don't have to pick them themselves. Now I will be going through the flow of our algorithm. The first step is to segment each track with Poisson L0 segmentation. The black lines are the L0 approximation of the tracks, and it works with row count data directly. And it is really fast, except for some pathological cases, it runs in linear time. And then we combine the breakpoints from every track into a single breakpoint set and calculate the segment means between breakpoints for each track. This way, we reduce the size of the data and minimize the effect of the noise. In second step, we combine the means from the current and two neighboring segments and the lengths of these segments for the clustering algorithm. We use Bayesian GMM with Dirichlet distribution as a prior for the component weights. The reason in this way, the algorithm drops a component if it is not needed for fitting the data by making its weight 0. And finally, we extended the labels we get from GMM back to the genome length. We evaluated FPseg with maximum fold change in 3 different categories and compare it with Segway, another genome segmentation algorithm that is very popular. For the signals that we use to segment the genome, FPseg did better for all tracks except for H3, K27, Me3. The H3, 27, Me3 has a low maximum fold change for both algorithms. And also, we also checked the enrichment for exon-intron regions. FPseg again outperformed Segway. Notably, we observed a 913-fold enrichment for the initial exon over Segway's 118. We finally checked enrichment for transcription factor PWM matches. We likewise find improved enrichment for all, but for transcription factors. In summary, we develop a FPseg that uses row count data. It utilizes a Poisson L0 segmentation that makes the algorithm very scalable, and it uses Bayesian GMM that drops unneeded components. Finally, we show that it is very competitive with the current state-of-the-art segmentation algorithms. Thank you for listening.